Hello, my name is Atharva Saranke, and today we're diving into something that affects every software developer but is rarely talked about how we mine patterns from millions of lines of code to make software better. Think of it as Google, but for your code base, uncovering hidden insights, detecting bugs, and making software maintenance easier. This presentation is based on the paper Comparison and Evaluation of Source Code Mining Tools and Techniques, a qualitative approach. I'll walk you through the key concepts, techniques, and real world applications of source code mining. Remember the Heartbleed bug from 2014? It's like the Thanos snap of cybersecurity, widespread chaos that could have been avoided. We'll see how source code mining could have caught it earlier. By the end, you'll see why source code mining is the Iron Man suit for every software engineer. Software systems today are growing unprecedentedly, making manual inspection and maintenance nearly impossible. Modern applications often contains millions of lines of code distributed across multiple repositories developed by teams spread across different locations. As software evolves, keeping track of dependencies, security vulnerabilities, redundant code, and maintenance issues become a significant challenge. This raises a crucial question. How can we efficiently extract insights from millions of lines of code? This question is at the heart of source code mining, which leverages data mining techniques to analyze, classify, and extract meaningful patterns from source code. The foundation of this presentation is a research paper published in the International Journal of Advanced Computer Science and Applications in 2013. This paper provides a comprehensive analysis of existing source code mining tools and techniques, highlighting their strengths, limitations, and potential areas for improvement. The core message of this research is that while various tools exist for bug detection, clone detection, API usage mining, and code change analysis, they often work in isolation rather than as an integrated solution. This lack of integration limits the effectiveness in large scale software engineering. Well, software development is not about writing new code. In fact, most developers spend a significant portion of their time understanding, debugging, and maintaining existing code. However, as the project grows, manually tracking code relationship, dependencies, and security risk becomes infeasible. Some of the biggest challenges in large scale software development include the sheer volume of code. Many large software systems, such as the Linux kernel or Microsoft Windows, contains tens of millions of lines of code. Understanding such vast code bases manually is unrealistic. There is interdependencies between the components. A small change in one file can trigger failure across multiple modules, making it difficult to predict unintended consequences. Code duplication and maintenance issues. Developers often reuse or modify existing code rather than writing from scratch, leading to a redundant or inconsistent implementations across the systems. There are security vulnerabilities hidden in legacy code. Bugs and security flaws can go unnoticed for years, sometimes resulting in catastrophic failures, as seen in major cybersecurity incidents. There could be outdated or incomplete documentation. In many cases, documentation does not accurately reflect code updates, making manual analysis even harder. A real world example that highlights the critical need for automated source code mining and dependency tracking is the Knight Capital Group trading disaster in 2012. Knight Capital, a major financial trading firm, suffered a catastrophic software failure that resulted in 440 million loss in just 45 minutes, ultimately leading to the company's collapse. The failure was caused by an old, unused software module that was accidentally reactivated when a new trading algorithm was deployed. This legacy code contained outdated logic that began executing thousands of unintended stock trades at high frequency. The system placed millions of unintended buy and sell orders, causing extreme volatility in stock prices. Because no real time code dependency tracking or automated error detection mechanisms were in place, the issue was not caught until it had already wiped out the firm's entire capital. This disaster underscores the importance of source code mining techniques, particularly code change analysis and bug detection. Had Knight Capital employed automated tools to analyze version history and detect unexpected interactions between old and new code, the system could have flagged this dependency issue before deployment. Additionally, mining historical software changes could have revealed the risks associated with legacy code and prevented the incorrect activation of outdated modules. Given these challenges, the key question this presentation will explore is how do we mine massive code bases efficiently? More specifically, how can we detect bugs, identify redundant code, track dependencies, and improve API usage automatically? Throughout this presentation, we will examine various techniques used for source code mining, from bug detection to code change analysis, and discuss how they can make software development faster, safer, and more efficient. Software is structured, logical, and full of patterns, kind of like the Matrix. Remember that iconic scene when Neo sees the code of the Matrix for the first time? Let's take a quick look at that.
Is that the Matrix? Yeah.
Do you always look at it and code it?
Well, you have to. The image translators work for the construct program. But there's way too much information to decode the Matrix. You get used to it. I don't even see the code.
Just like Neo, developers often stare at lines of code, trying to make sense of the patterns hidden within. But instead of dodging bullets, we are dodging bugs. Source code mining is a process of analyzing structured code using data mining techniques to extract meaningful patterns. It's like being a code detective, examining variables, functions, data structures, and program logic to detect recurring issues, optimize performance, and enhance software reusability. Think of it as Sherlock Holmes meets GitHub. Instead of solving crimes, we are solving bugs. Why does source code mining matter? Raise your hand if you have ever spent more time fixing a bug than writing the actual feature. Yeah, we've all been there. Code isn't just text, it's structured, logical, and full of patterns. These patterns can reveal security vulnerabilities, inefficiencies, and even future bugs. Traditionally, debugging was manual, making it slow and error prone. But now, with data mining techniques, we scan millions of lines of code in seconds. Well, in 2014, the infamous heartbleed bug in OpenSSL went undetected for 2 years, exposing passwords, emails, and sensitive data. It's like the Death Star having a tiny exhaust port that no one noticed until it was too late. If source code mining had been used, the pattern of improper memory access could have been flagged earlier. Well, how is this different from static analysis tools? Static analysis tools focus on individual files and predefined rules. Source code mining finds hidden patterns across multiple projects, making it more adaptable to unknown bugs. It's like comparing Google search to a library catalog. One's way more powerful. Let's look at some background and historical context. If debugging is the process of removing bugs, then programming must be the process of putting them in. Early debugging was painstakingly manual, like trying to fix a spaceship with duct tape. Then came static and dynamic analysis tools, which automated parts of the process. But as software scaled, traditional techniques failed to handle complexity. Enter data mining. Now we can analyze patterns across thousands of repositories to find bugs, inefficiencies, and duplicate code before they cause major problems. Think of it like Netflix recommendations. Instead of suggesting movies, it predicts where your code will fail. Well, how does this scale to large software projects? The answer is modern cloud based mining tools use distributed computing, for example, Hadoop, Spark, to handle massive code bases efficiently. It's like the Avengers assembling to tackle a massive threat. Let's look at the code mining process. The process of source code mining follows a structured and systematic approach. Much like extracting valuable minerals from raw ore, software systems generate massive amounts of code, logs, and version history, making it difficult for developers to manually detect patterns, security vulnerabilities, or inefficiencies. Source code mining automates this process by systematically analyzing structured code to extract meaningful insights. The first step in this process is data extraction, where relevant information is gathered from various sources such as version control systems, bug databases, and public or proprietary code repositories, for example, GitHub, Bitbucket. Additionally, execution traces and software logs can be analyzed to understand runtime behavior, which helps detect performance issues and inefficiencies. This step ensures that enough raw data is available to identify patterns in the later stages. Once data is collected, it must go through pre-processing where redundant, irrelevant, or noisy information is removed. This step involves tokenization, which breaks the code into fundamental units like keywords, variables, and functions. Additionally, an abstract syntax tree AST analysis can be applied to convert raw source code into structured format that makes it easier to identify relationships between different code components, removing unnecessary comments, boilerplate code, and unused dependencies further refines the dataset, ensuring that the mining process focuses only on functionality relevant aspects of the code. Following pre-processing, data mining techniques such as pattern recognition, clustering, and classification are applied to the clean dataset. Pattern recognition detects recurring code structures, which helps in bug detection, security analysis, and software optimization. Clustering groups similar code segments together, aiding in clone detection and refactoring recommendations. Classification techniques commonly used in defect prediction categorize code snippets into different risk levels based on previously mined data. Finally, the mine insights are applied to practical software engineering tasks. These insights can enhance bug detection, recommend code reuse opportunities, improve API usage, and predict potential vulnerabilities in the system. Let's look at some types of source code mining techniques. Well, there are several ways to mine source code, each with its own strengths and weaknesses. Bug detection tools like PR Miner and Chronicler find missing function calls and rule violations. Clone detection tools like CC Finder and CP Miner identify duplicated code to improve maintainability. API usage mining tools like CodeWeb and Prospector helps developer find correct API usage patterns. Finally, code change mining tools like Rose and Dynamine analyze historical commits to predict which files are likely to change together. Understanding these techniques helps developer choose the right tool for the right task. It's like having a Swiss Army knife for your code base. Each tool has a specific purpose. Well, if all these techniques exist, why aren't they integrated into one tool? Well, tool fragmentation is a problem. Researchers are working on hybrid approaches that combine multiple mining techniques into one system. Think of it as the infinity gauntlet of code mining. Once all the stones are combined, it's unstoppable. Let's look at bug detection. To illustrate the concept of bug detection, let's turn to a scene from Mr. Robot. In this clip, we'll see Elliot, a protagonist, delivering a monologue about debugging while lying in a hospital bed. Pay attention to how he describes the process of finding and understanding bugs.
Most coders think debugging software is about fixing a mistake, but that's bullshit. Debugging is actually all about finding the bug, about understanding why the bug was there to begin with, about knowing that its existence was no accident. It came to you to deliver a message, like an unconscious bubble floating to the surface, popping with a revelation you've secretly known all along.
Elliot's monologue perfectly captures the essence of bug detection. He says debugging is actually all about finding the bug, about understanding why the bug was there to begin with, and about knowing that its existence was no accident. This mirrors what automated tools like PR Miner and Dynamine do, but on a much larger scale. While Elliot manually scans through codes, these tools can analyze millions of lines in seconds. They use pattern recognition to identify potential vulnerabilities, much like Elliot describes bugs as delivering message or popping with a revelation. The key difference is the scale and speed at which these automated tools operate. That vulnerability remained undetected for 2 years in OpenSSL's codebase, exposing sensitive data worldwide. If an automated bug detection tool had been scanning OpenSSL's code, it could have caught the improper memory access pattern before the damage was done. The bug allowed attackers to retrieve private memory of applications using a vulnerable OpenSSL versions in 64K chunks. An automated tool could have identified this anomaly in the hardware extension implementation, potentially preventing the exposure of sensitive information like secret keys and user credentials. This underscores the importance of automated bug detection in today's complex software landscape. While skilled individuals like Elliot are invaluable, the sheer volume of code in modern systems necessitates automated solutions to complement human expertise. Now let's look at clone detection. Have you ever copy pasted code instead of writing it from scratch? Congratulations, you have contributed to code cloning. Cloning is common in software development, but excessive duplication can lead to bloated code bases, maintenance nightmares, and hidden bugs. There are three main ways to detect code clones. There's a string-based approach, which look for the exact duplicates. There's a token-based approaches like CC Finder, which recognizes syntax variations, and data mining-based approaches like CP Miner, which uses pattern recognition for the best accuracy. The goal is to strike a balance, reusing code effectively without creating unnecessary redundancy. In 2021, an AI-generated Stack Overflow response introduced a dangerous bug into multiple repositories. It's like the clone wars. Too many clones can lead to chaos. Let's move on to API usage mining. Well, APIs, that is application programming interface, serve as a building blocks for modern software development, allowing developers to reuse existing libraries and frameworks instead of building everything from scratch. However, using APIs effectively requires understanding their correct implementation patterns, which can be challenging due to incomplete or poorly documented references. API usage mining solves this issue by analyzing large scale software repositories to extract frequently used API patterns and best practices. By doing so, these techniques can help developers avoid incorrect API usage and improve software reliability. One of the most widely used API mining tools is CodeWeb, which mines large code bases to find common API usage sequences. Similarly, Prospector recommends method sequences by analyzing how APIs have been used in existing software projects. Strathcona, another API mining tool, takes a structural approach by finding API usage examples that match a given program structure. These tools collectively enable developers to write better code by learning from previous implementations. Well, a real world example of API mining is its integration into GitHub Copilot, which leverages API mining along with machine learning to auto generate code snippets that align with commonly used patterns. However, API mining is not foolproof. If a dataset contains incorrect or suboptimal API usage patterns, the tool may reinforce bad coding practices. This highlights the importance of maintaining high quality training datasets. Well, one possible question that could arise is, can API mining suggest bad practices? The answer is yes. If a dataset includes poorly structured API calls or inefficient code, API mining tools may unintentionally propagate those patterns. To mitigate this, researchers are working on improving context awareness in API mining techniques to filter out irrelevant or incorrect recommendations. Moving on to mining code changes and bug fixes. Software projects often involve multiple interdependent components where modifying one file may require changes in others. Code change mining is a technique that analyzes historical version control logs to predict which files are likely to change together. This is particularly useful in large scale projects where missing a dependent change can introduce new bugs or regressions. For example, consider a scenario where a developer updates functions that interacts with a database but forgets to modify the corresponding data validation logic in another module. Code change mining can identify this pattern based on historical commits and suggest related modifications to avoid incomplete fixes. Among the key tools discussed in this paper, Rose mines version control logs to identify code changing files, while Dynamine focuses on function call violations using past software revisions. Another approach uses CVS change logs to recommend related file modifications, further improving code maintenance efficiency. A real world example of code change mining in action is its application at Facebook, where the tool is used in the pull request system to detect potential dependencies between code changes before merging them. This reduces the risk of introducing unintended errors into production environments. Well, a common question might be, does code change mining replace code review? The answer is no. While the code change mining provides automated recommendations, it does not eliminate the need for human judgment. Instead, it serves as a supporting tool that enhances developer awareness of hidden dependencies, making manual code reviews more efficient. Well, let's check some data mining techniques in the source code mining. Different data mining techniques are employed to extract useful insights from source code, each with its own strengths and limitations. The paper categorizes functions into frequent pattern matching, association rule mining, graph mining, clustering, pattern matching, sequential pattern mining, and classification. Well, let's look at frequent pattern matching, which identifies recurring patterns in the code bases, helping to detect common code structures or bug patterns. Association rule mining finds a relationship between software components such as API calls that frequently appear together. Graph mining analyzes structured relationships within code, such as function call or class hierarchies. Clustering groups similar code structures together, which is useful for detecting refactoring opportunities. Pattern matching compares code segment to predefined templates. It is commonly used in bug detection. And sequential pattern mining identifies common execution sequences in the code. Classification labels code segments based on learned features often used in defect prediction. Well, a real world example is the Google's bug prediction model, which combines classification and frequent pattern mining to detect potential vulnerabilities in Chrome's codebase. By analyzing past commits, the model predicts which changes are likely to introduce defects, allowing developers to proactively address these issues. Do these techniques work for all programming languages? The answer is that while some of the techniques, such as frequent pattern mining and clustering, are broadly applicable, others like graph mining and pattern matching depend on specific language features and may require adaptation for different ecosystems. Quickly look at the comparison of tools and techniques presented in the paper. Well, different source code mining tools excel in different aspects, making it more important to understand their comparative advantages. The paper presents a side by side comparison for various tools, focusing on bug detection, API mining, clone detection, and code change analysis. For instance, PR Miner is highly effective for detecting bugs caused by function call violations, whereas CP Miner is specifically designed for detecting duplicated code. On the other hand, Prospector and CodeWeb focuses on API mining, helping developers adopt correct usage patterns. Rose and Dynamine stand out for their ability to identify code change dependencies, improving software maintainability. A key takeaway from this comparison is that no single tool excels in all areas. Instead, a combination of multiple tools is often required to comprehensively analyze a software project. This highlights the need for future research into hybrid approaches that integrate multiple mining techniques into a unified framework. One likely question is, why isn't there an all in one tool for source code mining? The answer is that different mining techniques require different computational models and optimization strategies. While hybrid approaches are emerging, the complexity of integrating multiple methods without compromising the performance remains an open research challenge. Let's look at some challenges and future directions. Despite the advancements in source code mining, several challenges remain. One major issue is scalability. Processing large scale software repositories requires significant computational resources, and existing mining techniques may struggle with performance bottlenecks. Another challenge is false positives, where tools may flag issues that are not actual bugs, leading to unnecessary developer effort. Tool integration is also a concern, as most current solutions focus on a single aspect of software analysis, requiring developers to use tools to get a complete picture. The paper suggests that the future research should explore hybrid mining approaches that combine multiple techniques to provide a more holistic analysis of software projects. Looking ahead, AI powered source code mining is expected to play a major role in automating software quality assurance. Machine learning models trained on vast code repositories can improve bug prediction accuracy, suggest optimal refactoring strategies, and even auto generate patches for detected issues. Automated security patching, where historical vulnerability patterns are used to predict and fix security flaws before they are exploited, is another promising direction. A common question is, will AI replace human developers in debugging? The answer is no. While AI driven tools enhance developer productivity, human intuition and domain expertise are still crucial for making high level architectural decisions and interpreting complex issues that automated tools may miss. Let's look at some key takeaways from this paper. To summarize, source code mining has transformed software development by automating bug detection, improving code reuse, and enhancing maintainability. Bug detection tools like PR Miner prevent software failures, while clone detection tools like CP Miner ensure cleaner and more maintainable code bases. API usage mining helps developers adopt best practices, and code change analysis reduces regression risks in larger projects. However, the field is still evolving, and there is a strong need for integrated mining tools that combine multiple techniques into a single solution. AI driven approaches are likely to play a key role in this evolution, offering real time code analysis and self healing capabilities. For developers, staying informed about source code mining techniques can lead to higher quality software and faster development cycles. That's it from my side. Thank you for your time. If you have any questions, feel free to reach out to me. Also, I'd love to hear if you have ever encountered a tricky bug that could have been caught by one of these techniques. Let me know in the comments. Thank you.